Are you able to see my slides now? Yeah, just the gray.
It's just like gray background.
Oh yeah. Okay. Good. Right. So let's get going. We are done pretty much for this course as far as the geometry is concerned. We will visit certain other aspects of it later on. Right now, we'll get into the second most important aspect of the structure, whether we are analyzing or designing it, is the material. If it's design, then it's material selection. Otherwise, if it's an analysis to just to know what materials the structure that we are analyzing is made out of, because it's usually not just a single material, it's a combination of materials. So we need to know the not only the materials and their properties, but also how they are distributed across the structure, right? So whatever it is, whether it is analysis or design, we usually check for at least three things. And the first amongst them is to see if, let me see if this works. Yeah. Right. So the first thing that we check out for is the whether the all the materials are safe. In other words, there's no impending failure under the typical kind of loads that the structure will be subjected to, even at the extremes of the flight envelope that we were talking about, the VN diagram. So that's called the strength-based design. And as a mnemonic, all three are starting with an S. The second one is stiffness-based design, and the third one is stability-based. And it's not that we choose one of these. It's essentially a combination of these. Sometimes one might be more important for a particular component than the other. Then the other two might be used as constraints, and one might be used as the one which we would optimize for maximum performance. Why is stiffness important is the fact that even though the material might not be failing, the structural component might be having a very large deflection. And if it is having a very large deflection, then sometimes it could be deleterious to the aerodynamics because the overall aerodynamic shape might change. Sometimes if it's on the ground, then it might certain parts of the, let's say, the tail rotor or the tip of the fixed wing might be touching the ground, which could again be deleterious. So we really want certain cases the stiffness to be taken care of as well. It should be above a certain value, and that's why we need a stiffness-based design. This is important not only from the point of view of statics, as we shall see in today's class. It's very important from the point of view of dynamics, and we've already seen that since it's a vehicle, the aerospace vehicle is subjected to a lot of dynamic loads, and the dynamics is strongly affected by the stiffness. In fact, in your very basic course on structural dynamics or vibrations, you'll know that for a single degree of freedom system, let's say just a spring and a mass, spring constant, which is linear value of K, and mass of M. Even in that, the natural frequency is given by square root of K by M. So you see that the stiffness K plays a very important critical role there. And so we will also see why the natural frequency is important when we get there. Now, that's the second aspect of the design as far as the material selection is concerned. And the last one is stability. We will see it from the perspective of elastic stability, that is to avoid buckling or to delay buckling. But as I said in the previous class, sometimes we would like to operate in the post-buckling regime as well, but that's only for certain components like the skin of the wing or the fuselage. Many times there are other members subjected to compressive loads as well, like the stringers on the top portion of the wing, and those should not buckle. So we need to ensure that through a stability-based design. So these are the three categories, and we will look at them one by one. But before we get into each one of them, we will talk about a few things related to materials itself. especially set the background for composites, but by looking at certain things that you've already learned as part of your previous course, it's more like a very high level summary of whatever you've learned in that course, just through a couple of slides, where we will look at the typical materials that were being used predominantly prior to the advent of composites, synthetic composites, and amongst them, the ones which continue to be used in smaller quantities, even in today's aircraft, or will continue perhaps for the next couple of generations of aircraft the way it stands, right? So can you just mute your microphone? And you can turn it on whenever you need it. Yeah, thank you. Next, let's look at the material selection aspects. As far as the selection of the material goes, as I already mentioned, it's a very important part of structural design. And for analysis, you need to know what materials are there and what are their properties. Otherwise, you'll not be able to carry out a reasonably good analysis, which gives results of any significance at all. The important thing is there are many different properties of materials, and a large chunk of them are physical properties. But even amongst physical properties, not all are of great relevance to structural analysis. Like, for example, some of the electrical properties and or magnetic properties, etc., may not be of much significance over here, or even the optical properties, etc., unless there are some additional functionalities for the material. So the main properties that we will be concerned with as far as structural analysis or even design is concerned, we will see from the perspective of three important metallic materials that have been used traditionally and continue to be used in reasonably good quantities for different kinds of aircraft. One is the set of aluminum alloys. Again, there's a very broad range of aluminum alloys. We will visit a few of them in a later class, very briefly. And then typically for higher temperature applications and or a little more stringent applications, in especially in military aircraft, you use some titanium alloys as well. And finally, of course, steel in much lesser quantity compared to the aluminum alloys, at least. So the pictures on the top essentially show an example of an aluminum alloy, typically how it looks, titanium alloy and a steel alloy of various compositions. Again, the lead element, of course, is aluminum, but there are many different alloying elements that come along with it. Similarly, the lead element here is titanium, whereas for steel, as you very well know, it's iron alloyed with many other materials. So it's not just the combination of materials and their percentage values, but also the manufacturing processes, in particular the heat treatment, etc., which determines the properties. As I said, there are three important properties, physical properties, that we would like to be focused on as far as structural analysis is concerned. So let's get started with that. The first one is the ultimate tensile strength, which we will denote by sigma u. Though this is important, an equally important parameter is also the ultimate compressive strength. Just this is called, also sometimes called as UTS. That one is called as UCS. So right now, to avoid too much of a complication, let's focus on tension alone. And so here we are just talking about tension. That is the UTS, though that's not specifically mentioned in the symbol sigma U standing for ultimate. Truly speaking, there should be a plus sign as a superscript to show that it is a UTS rather than a UCS. And a typical SI unit that is used with this is megapascals, which is 10 power 6 Newton per meter squared. Or alternatively, you can write it as Newton per millimeter squared, because 1 millimeter squared is 10 power minus 1 millimeter is 10 power minus 3 meters, and therefore instead of a mega, you put, instead of meter squared, you put a millimeter squared, takes care of that unit. And that's what is typically used in a lot of software as well as a standard. So these are interchangeable. It's very important for you to know whether it's megapascals or Newton per millimeter squared. Without any multiplication of any factor, you use it as it is. Coming to aluminium alloys, again, as I said, there are a large class of aluminium alloys, so there will be a wide range of sigma U's for them. But we are only looking at relative values and also some ballpark values. So the one that is given in your in what is considered to be a textbook for this course, though we don't use here at IISc. It's something that if somebody else at Georgia Tech were teaching this course, they would have perhaps used Bolshow and Craig. I took a course with Bolshow, so some of you see some flavors of that coming through this, but at that time the textbook was not around. So my slides, though uniquely presented in my style, is actually based on information from Bolshow's class notes that I had. Okay, so this is as far as aluminium goes. Next is titanium alloys. So a ballpark value for that is 1900 Newton per millimeter squared as the ultimate tensile strength. So you already see almost 3 times or a little more than 3 times the aluminium. So you see if you're looking at it purely from a tensile performance all the way to failure. And remember, ultimate tensile strength is beyond the proportionality limit and the also the yield strength, and therefore it's already gone into the plastic regime. This is the final failure of the material. You rarely will go all the way up to it, but just important to be aware of these numbers, not exactly, but at least in terms of an overall idea of relative sense. Okay, so that's 3 times, and then you see even more than double of that titanium, and therefore about 6 or more times, or 6 to 7 times of the aluminium is what you have as the typical value for steel, 4100 megapascals. Again, there's a huge range. This is for this is typically on a higher side, but we will see typically in the auto grade, you will see a fairly wide range of steels used for automobiles, and we will see the current state of the art there in terms of the range, both in terms of sigma U as well as the elongation, because that's also important when you go to other things that we want to know. So from this perspective, it's very, very clear that steel is a winner by a very big margin. So if this were all the criteria that were to be used to select a material for a particular component, let's say the landing gear, then obviously this is a clear winner. But that's one of the very few areas which still remains the realm of steel, whereas most of the places, if not composites, it's been replaced by either aluminum alloys or titanium alloys. So obviously there should be something in favor of these two guys, the aluminum and the titanium, which in spite of such a huge performance of steel, we continue to use these. And that's what we are heading towards. Obviously, you know the answer to that, but let's go about it in a little more systematic manner over here. Okay, so let's check out the Young's modulus. Remember that we're dealing with metallic alloys here. So whether it is metals or metallic alloys, they're typically isotropic, in which case either whether it's the tensile strength or the Young's modulus, I don't need to specify in which particular direction is this property, because it's the same in all directions for that given alloy. Once the alloy is specifically chosen, that's what it is. Okay. So again, you see a very, very similar gradation as we saw in the case of the sigma U. So as far as aluminum is concerned, a typical ballpark value. And here there's not as much of a spread in the range of values. Sigma U values can vary between the aluminum alloys, specific choices of aluminum alloys quite a bit. But E, the Young's modulus, doesn't vary as much. Even before that, we need to be sure we took a note of the units that we are using here for E, which is gigapascals rather than megapascals, which is 1,000 megapascals. So it's a much, much larger quantity that we are talking about compared to sigma U. And that's kind of clear because, as you might recollect, the Young's modulus is nothing but the proportionality constant in the linear limit between the stress and the strain, the tensile stress and the tensile strain. And that slope is usually a fairly large number, because the stress is very large, at which the limit is reached, the proportionality limit, which is of course much smaller than the ultimate tensile strengths or even the yield strength that we saw a little earlier. But nonetheless, the elongation at that level is typically, for most metals and metallic alloys, is of the order of a few percentage. So it could be of the order of 1%, 2%, 4%, 5%, etc. Around. So just in terms of orders of magnitude, it's the non-dimensional value is 10 power minus 2. So which means that you're dividing that quantity, whatever we saw in the previous row, that is the sigma u's, or a much smaller value of compared to that, which is the sigma proportionality limit, by that particular failure limit in order to reach this slope. So that because you start with 0, 0. So that's the slope of that particular sigma versus epsilon curve, in particular sigma, a normal stress versus a normal stream along the same direction. Right. So that's why the E values are typically much, much larger compared to the sigma U values. But that is, instead of taking care of it in the numbers, you're taking care of it by changing the unit over here. Alternatively, I could have given this also in megapascals and put this as 73,000, right? So then you will see how much bigger it is compared to the sigma U, corresponding sigma U's that we already saw. So here, as I said, there's not much of a range across the aluminum alloys, but you see about 1.5 times that is what titanium alloys are. Uh, so the relative change is not as much, and steel is about double of that of titanium, and which means about 3 times that of the aluminum alloys. And so once again, you see a similar trend that is there, that that we see that titanium is better than aluminum and steel is better than titanium, and therefore I'm highlighting the last column here, both in the case of the sigma U as well as the E, that is the Young's modulus, right? So let's get going. So now the inference from both those rows. So the first row that we saw was that the ultimate tensile strength are in a descending order given this way. That is not exactly descending order, but essentially I'm saying which is the largest amongst them, and which is it large compared to. That is, for steel, it is much more than for aluminum and or titanium. The other thing, of course, is clear. Similar conclusion is there in terms of the Young's modulus, or E as well. The stiffness, as we call it, and stiffness for steel is much larger compared to that of aluminum or titanium. So that's fairly clear, and this is something that you have known before as well. And therefore, you see that steel is obviously the strongest as well as the stiffest material. So we always want to know. We want to know that in spite of that, why is steel not preferred always? And as you already are aware, it's because it's a weight critical design in any vehicular structure. In particular, in aerospace, it becomes even more critical, the weight, and therefore we don't need to, we should not be looking at only the absolute values of sigma U and E, but in some sense the material density also factored in into that. So first of all, we will see the densities in an absolute sense, and then we will see how we can combine this with the properties we saw on the previous slide. So once again, it's the same set of 3 materials: aluminum alloys, titanium alloys, and steels, which are iron alloys, to be more specific, in the same nomenclature. So now we come again with SI units for the densities in kilograms per meter cube. And here you see the gradation is exactly in opposite direction. So what was in the ascending order continues to be in ascending order, but that it was a preferable quantity on the previous slide. That is, the 2 quantities we saw, sigma U and E, were the higher the better. Whereas here for rho, we know that the lower the better. Okay, and the lowest value is 2,700. So here again, this is the highest, but that's actually not desirable. Right, the lowest is desirable over here, and it's the same order in which the preference goes as far as the increase is concerned. But in terms of the choice of the material, we would rather choose aluminum over titanium and titanium over steel. Okay, but since these are two different quantities and we want to be, or rather three different quantities that we talked about, and we want to have some kind of a common plane on which we would like to look at these, it's the question, of course, is steel isn't always preferred because it's far heavier. So that's purely from the absolute values of the density. But again, this has to be taken with a pinch of salt. We will see why that's so once we get to the even the specific properties. As I said, the specific properties are taking into account the density factored in some way into the sigma u and rho, the ultimate tensile strength, and the Young's modulus intention, right? So in a weight sensitive design, the compromise is always between a few conflicting characteristics. Something might go up, something might go down, something might be desirable, something might be undesirable. So you'll always have to make a compromise. In other words, go walk the in between line. So then we will see, because purely from density, we saw aluminum is the winner, and purely from either sigma U or E, we saw steel is the winner. So we want to see between these three materials. So we have not yet introduced composites, but we want to see how we can probably compare the choices that we have. Okay, so now we need to compare material properties for different structural applications. We have seen in the various classifications that we had, not in the previous class, but the class last Thursday. We saw that there are various specific applications that we have, and the material performance needs to be compared across them. So when we do that, there are three primary categories of the situations for which a structural member is designed. Not only one of them, but sometimes two or all three of them as well. So as we already saw, these are the three words starting with S, namely strength, stiffness, and stability. So we will take them one by one in the way Olivier Borschow does in his book with Craig. Okay, so now the material performance indices need to be derived for each one of these. I've already mentioned in passing that sigma u by rho is the specific strength in one of the earliest classes itself, very first week, and we also saw that E by rho, which is the Young's modulus by the density, is the specific stiffness. But that was just taken for granted at that point in time, but and it made some kind of a logical sense for us, but we want a more clear derivation from the point of view of structural analysis. Without going into the full details of the derivation, we will see a few steps of the derivation in order to understand it, just the way Olivier introduces these concepts as well. When he was at Georgia Tech, but later on he went to University of Maryland, and a few years he spent in China and various other countries, including Finland, etc. Now back in the US, but excellent, one of the excellent teachers for structures and composites as well. Okay, so now let's get going with the strength-based design. And while I'm doing this, I'll also take advantage of the fact that here we are talking about the three different categories. So instead of using the same structure for all three of them, what I will do is try to see if I can use different kinds of structures for each one of them, so that we can then introduce other concepts also simultaneously. So that's what I'm trying to do over here. So what I will do to start with is just to take a thin rectangular strip, but it could have a pre-twist, as it does in the case of a fixed wing aircraft in the form of a wash in or a wash out. Uh, are you able to see, oops, the aircraft that I'm showing you here? Yeah.
Yeah, we can see it.
Okay. So you recognize which aircraft this is? It's an Airbus aircraft, but which particular Airbus? I'm covering the name, I guess. Yeah, absolutely. So Uh, uh, Many people may not have seen this. Essentially, it is used to carry different parts of the aircraft from wherever they are made across the world. Because remember, today the way the entire aerospace ecosystem manufacturing OEMs work is they manufacture different parts of the aircraft in different parts of the world and eventually bring them together at a particular assembly line and they assemble them all together and so such large parts, instead of shipping them all the time, many times can be carried if they're not that big, but reasonably big. They can be carried by this particular aircraft, the Beluga, right? So now if you look at this, if you look at the wing over here, there's a small angle of this, which is the wing tip is facing a slightly higher angle of attack compared to the root. And this is kind of common. There are other designs where it's exactly the opposite, what we call as the wash out or the wash in. And this is even more common in the case of helicopters, where you would have pre-twist in the rotor blade. And so either case, what would happen is that that cross section, wherever you take, it will make different angles with respect to fixed frame, let's say an aircraft fixed frame or fuselage fixed frame of reference. So keeping that in mind, we introduce certain coordinate systems over here. So I'm sorry if the background is not very clear over here because of my video out here. What we're talking about is a rectangular strip of length L. The nomenclature is kind of self-explanatory. L for length, B for breadth, or you can call it width as well if you want, and H for height, which is essentially the thickness of this element, right? So now sometimes we will use T, but here it's just to be clear about length, breadth, and height. L, B, and H are used for them. Okay, so along these three directions, all these three dimensions, we introduce coordinate measures, which is x1 along the length that you see over here. And tangential to that x1, you will have a unit vector, which is b1. Uh, Unless otherwise mentioned, bold letters will represent vector quantities, whereas those without bold, the normal font, regular font, or italicized, will typically represent scalar quantities. Okay, so you have x1 times b1 as the vector going along this because there's no initial curvature that is shown over there, but there is an initial twist, or what I just mentioned as pre-twist, washout, or wash in, depending upon whether it's helicopter terminology or the fixed wing aircraft terminology. So similarly, we will have a quantity x2 is the coordinate measure along the width, and B2 is the unit vector over there, right? Then along the height h, we have the coordinate measure x3 and the unit vector tangential to that coordinate curve is b3. Now you see, whereas b1 is a constant, your b2 and b3 in this particular case are functions of x1. Why? Because there is a pre-twist, right? So because the different cross sections are making a slightly different angle with respect to each other, and which means that depending upon where you take that particular cross section, here or here, it is going to be at a different angle, and therefore you see x1 is the coordinate measure along the length. So depending on where I take the cross section, b2 and b3 will have a different direction. Of course, they are unit vectors, so the magnitude remains one, but only their direction changes slightly. Right. So this is the element that we will use here for the stiffness-based design and the stability-based design. We will introduce two different other kinds of structures. So it doesn't matter what structure I introduce, because essentially we are going to hit at material properties. But I'm taking this as an opportunity to introduce certain typical configurations that are used in aerospace, so that uh, we essentially get multiple benefits while doing the same thing. I think one of you was talking about mangoes during our meet and greets session. So there's a typical saying in the local language here, "Ore kallila rendu manga," essentially means that with a single stone you hit, you get two mangoes falling from the mango tree. so that you don't need to have to expend more efforts to get more mangoes. So you essentially get multiple mangoes with a single throw. Same way, because our time is limited, in terms of the overall number of hours we have for this course, it's not possible to go into everything in detail. So we will try to see if, while introducing certain concept in this slide, for example, our primary goal is to introduce the strength-based design. So that is our primary goal. But at the same time, I'm introducing to you a typical kind of a model for either a very high aspect ratio wing, or a tail rotor blade, or even a main rotor blade, and also the typical kinds of complications that are there in some of them, right? There could also be, going forward in the future aircraft, some even B1 becoming function of X1 if you have initial curvature, which is kind of rare, but already you have certain aircraft for which the sweep is twofold. So in this case, you see there is a taper, but also in terms of the leading edge, there's a single angle over here for the sweep. But if you're looking at the line joining all the mean aerodynamic center, because of this discontinuity you have at this particular point, you will see that that uh, loci of the mean aerodynamic center will not be a straight line, but it will be piecewise linear. And so there will be a kink at this particular point where there is a slight change in the overall taper ratio, right? So when you have things like that, you would have B1 constant, a particular value of B1 till here, and another value of B1 up to here. So B1 changes with X1, but not in a continuous manner, but in a piecewise linear manner. Okay. So I hope the coordinate system and the dimensions, the notations are clear here, because those will be used for the simple derivation that we are going to do next. You can unmute and say yes or no, or ask any questions.
I think it makes sense.
Okay, thanks. So let's get going here. As we already mentioned, for the strength-based design, the main thing that we are looking at is the failure of the material. That is the criterion. Uh, Again, it's a very, very large topic. As I said, failure. You could have multiple courses just on failure for different kinds of materials, metals and composites. But here we're focusing on metals to keep things simple. Later on, we'll generalize this. So that's the material failure. That's the criterion. So now we are considering like a metal sheet over here. You mentioned metal sheet in one of the second assignment as well that you presented on Monday. And in this case, that sheet metal is subjected to just tension, and tension which is uniaxial. We say either uniaxial, biaxial, or triaxial tension, referring to the fact that the structure might be loaded just in one direction, or simultaneously along the length and along the width, or maybe even along the thickness. Okay, so in this particular geometry that we are seeing over here, it's a special kind of a geometry where you can either deal with it as 3D like any other body. You can deal with it as a plate, because h is small compared to the thickness h is small compared to the breadth b and the length l. At the same time, b is also small compared to the length, and therefore it can even be treated as a beam, though it's a much stubbier beam than what you typically see, right? So it's purposely chosen this way so that we can introduce multiple kinds of concepts over here. For example, if you're dealing with this as a plate, then the x3 direction that you see over here, this x3 becomes the shortest dimension, because it has the range from going from minus h by 2 to plus h by 2 along B3, right? So that the total distance traversed through the material is minus h by 2 to plus h by 2 is h. So you see that is the smaller dimension. So anything along that dimension will be called a transverse quantity if you're dealing with this as a plate. If you're dealing with this as a beam, yes, this will be a transverse quantity. In addition, you will have even your B2, also B2, also a direction of a transverse direction, because that's also a smaller dimension, B, compared to the length L. Okay, so your X2 dimension that you have over there. Are you able to see the X2, B2 over there, or is there something blocking your?
We can see the X2 and X3. I think the X1 is kind of blocked, but
Okay,
we
okay. So this one,
are
yeah, yeah, because of the video. Okay. That's right. Yeah. In my case, the top is blocked as well because I'm getting something related to the Teams. So that's why I asked. So right now I'm focusing on X2 and B2. And if it were a plate, then this would be a one of the two longitudinal directions. Whereas if it is the modeled as a beam, then this will also become a transverse direction, just like X3, B3. Okay. So because both of these are smaller dimensions, and the smaller dimensions will have a different kind of a behavior compared to the larger dimensions. So in both cases, whether it is plate or beam, your x1, b1 will be a longitudinal direction. So in this particular case, we'll consider a uniaxial loading along x1, b1. So our load is parallel to b1. Okay. Next thing, it's always important hereafter in all the homeworks that you're going to be presenting as well, the solutions for. I've already talked to you about the game rules. One of the game rules was to state the assumptions upfront wherever they are invoked. Uh, Rather than all together at the top or all together at the bottom, it's only wherever they are invoked. So if you see that here, I'm saying that the stress distribution is uniform because I'm going to be talking about a load, and then I'm going to see how that load is getting distributed as a stress, because the load, as I always say, in from the Newton's third law terminology or parlance, it is uh, an action, whereas the stress is the reaction of the material to that action, and we want to assume that that stress is distributed uniformly. And we already invoked a particular principle called the Saint Venant's principle to help us out, so that if you go a distance which is of the order of the thickness of this plate, then in the interiors of this plate, it really doesn't matter how exactly you're applying that particular load here. The so-called concentrated load might be applied at x2 and x3 equal to 0, which is the origin at that cross section. So it could be applied along that, or it could be a distributed load and distributed either uniformly, or it could be distributed in a linear fashion, whatever it may be. Because you know that in the actual aircraft, the lift distribution, drag distribution are all coming from the pressure and shear distributions, the shear in the boundary layer in particular, and therefore the actual distribution is not uniform, but it doesn't matter in the interiors. Thanks to Saint Venant's principle, it's proven that if you go slightly from the border, that is from the, you know that this is x1 equal to L and this is x1 equal to 0, this particular cross section here, the extreme cross sections are x1 equal to 0 and x1 equal to L. Right. So from if you're a little into the interior from those two ends, then you'll see in all of these portions which are highlighted right now, you would see that it really doesn't matter how the actual load is applied at the two ends. In our case, it's approximately fixed end over here and an approximately concentrated load here for the simple example that we are taking. But the aircraft example, or in particular, let's say the helicopter rotor blade, where you have a centrifugal force, which is a distributed force rather than a tip load along the axial direction. The conclusions or takeaways at the end of this slide will remain the same, but as far as the exact derivations are concerned, there will obviously be more complications involved, but we will end up with the same result. So we are not overly complicating the whole thing, but I'm just mentioning to you the differences to notice. Okay, so this is the assumption that we are going to make. Since it doesn't matter how you're going to have the actual load, we can assume in the interiors over here that the stress is uniformly distributed. Okay, so what does that mean? It means that the total load carrying capacity of this, because remember, the criterion that we are looking at is material failure. So in other words, it's a strength-based design. So I'm going to apply a load at this point. which is along the B1 direction. So it's essentially an axial load and axial tension. As I said, it's only along that direction, and therefore it's a uniaxial tension. And when I'm applying a uniaxial tension, you can think of it, for example, in a UTM that you might have seen in some of your labs, the uniaxial testing machine, where one end is fixed and the other end there's a load cell which is trying to pull this apart. And that's essentially what we are talking about over here. When this is pulling apart, you slowly start increasing that value of that load so that it goes beyond proportionality limit, beyond the yield of the material, and eventually to the ultimate tensile strength at some point, because of which a crack originates and a fracture takes place. And typically, of course, the specimen that you'd use in a UTM is not exactly rectangular like this. You'll have a dog bone kind of a shape, and there are certain regions which are more susceptible to damage, and that's where you'll typically have the fracture, right? So coming to the thing that we're trying to determine through such an experiment is to see what is the maximum load it can take. So that's why we're calling it a total load carrying capacity of this structure. So we will denote that load that we are applying over here along the x1 direction, v1 direction, to with the letter P, uppercase P. And so we are slowly increasing P all the way from 0 until ultimate tensile failure occurs for this specimen, which means that we have reached the so-called P max, and obviously the stress has reached sigma u. And even though it might have reached only at certain points, because of our assumption of uniform stress distribution, theoretically speaking, it's sigma u throughout a particular cross section, or any cross section for that matter you take, and therefore uh, it will be that stress times the cross sectional area, which in this case the width is b, as we saw over here, and we saw that the thickness that we are denoting by h over here. So the cross sectional area is breadth times height, P times H, multiplied by the uniform stress that is reached. Once P has reached its maximum value, sigma also has reached its maximum value. Truly speaking, this sigma has to be written as, because it is on the one phase in the one direction, so it has to be written as sigma subscript 1, 1, to denote that it is acting on the one phase, that is the phase to which B1 is the normal, and parallel to B1, therefore the second subscript is also 1. Okay, but what we are talking about is purely from a material point of view. So the scalar value at which this occurs is the material failure criterion for such kinds of materials, which is the ultimate tensile strength, sigma u, and that's multiplied by the cross-sectional area. So is this first equation clear? Are you with me?
Yeah.
Okay. So the other aspect here is, if it were just let's say a civil engineering structure, then I would have stopped with this. Let's say reinforced concrete, like you use the analogy in the case of the hare and the tortoise, then we would be done pretty much at this stage. We'd not be looking at anything else. But since it's a vehicular structure, whether it is naval or marine on the one hand, railway on tracks, or automobiles on the road, whatever it is, or even ships and yachts, etc., on the ocean, you will see that another important quantity is the structural mass, and even more so for aerospace vehicles. So we will look at that as well. And again, for this kind of a structure, it is very simple. We'll assume that the K1, which is the pre-twist that is there for this, is fairly small. So this can be thought of as a cuboid, and a cuboid of length L, breadth B, and height h. It's very clear that the volume is the product of all those three, LBH. And if the material is a single material that we are using over here, it has a single mass density rho, and just the product of that density with the volume should give me the total mass. And that's what you see in this particular second equation over here, where we are saying that M is equal to, where capital M is used to denote the structural mass in this particular slide. We will use it for other purposes later, and in which case we'll use a small m for this. But right now, using the capital M, and so the density rho times BHL gives you that. So on this particular slide alone, I'm using a highlight in blue to denote the material properties, whereas those that I've not highlighted, like B, H, L, etc., both in both the equations, equation 1 and 2, are quantities that you can clearly see are geometric quantities, whereas sigma, u, and rho are material properties. And our focus, at least in today's class and a few classes after that, will be, maybe for this week, will be on the materials aspects, and therefore those two quantities are highlighted. So in the first few slides we were looking, and in fact the second slide we had today, we just looked at sigma u alone, along with E, of course, and in the third slide we looked at rho alone, but now we are looking at both of them together. Though they're still in two different equations, eventually we would like to combine them. Now, coming back to our analogy with the actual aircraft structural component, as I said, this could be a helicopter rotor blade or a wing, in which case the dimension L that you see along the x1 direction over here, parallel to B1, is like this semi-span. So if the span of the aircraft is given to us, which is essentially the distance from wingtip to wingtip, then half of that distance, which is essentially the length of one of the wings, either the starboard or the port, then you would see that semi-span is what we are denoting by L over here, the length. And it's quite clear that that is something that we as structural engineers don't have a play around with. In other words, the aerodynamicist will dictate that based on the planform area and the aspect ratio that is chosen for the appropriate aerodynamics of this, based on its requirements, what is its payload, what is its the speed at which it is going to be cruising, at what altitude it is going to be cruising, what is its range, etc. These are the kinds of things from which requirements from which you will be determining the overall sizing of the wing, and therefore L is something that you and I, as structural engineers, cannot play around with. Similarly, if you look at B, this quantity here, the breadth, in the case of the wing, it is nothing but the chord. So the chord, of course, it is tapering in this case. We are considering a very simple case, which is also true for some of the lower speed aircraft, where you can have without taper. So you would have the chord which is fixed. Now that chord that is there is also an aerodynamic feature. So just for that kind of an aircraft, of course, like this, you would have B times L, the breadth times the length, which is the chord times the semi-span, is half the platform area of the wing. That is essentially the area of the wing as you see from the top or from the bottom, right? So in these two equations, we come back to, we see that there are many quantities on the left and the right hand side, of which you can see that B and L are quantities over which we as structural engineers do not have a play. So only thing that we can change is H. That is the thickness of the material that we are going to use, the sheet metal. Remember that we are talking about here. That sheet has a thickness H that we are talking about here. That H we can play around with because it's only the outer geometry that is fixed by the aerodynamicist. The inner geometry is up to us, and therefore we can play around with H. And we can play around with the material that we choose, and therefore sigma, u, and rho also we can play around with. Now coming to these two quantities on the left-hand side, this is the maximum load. So we would want to maximize that so that our performance is as good as possible, or it might be dictated to us. But on the other hand, the mass, we already saw, for example, that the compared to the gross takeoff weight of this entire aircraft, the structural weight, that is the weight of the fuselage skin, fuselage stringers, the fuselage bulkhead, the wing skin, the wing spars, the wing, which includes, of course, the cap and the web, the wing stringers or longerons, and then similarly for the other lifting surfaces, namely the vertical tail and the horizontal tail, the stabilizers that you have, also winglets like you have in this particular case on the tail. So all of those are the structural weight, constitute the structural weight, and that we saw we are given an allowance compared to the overall weight of the aircraft, which is the maximum takeoff weight, the gross weight. Compared to that, 20 to 25% is at our hands, and that 20 to 25% has to be distributed between the fuselage, the stabilizers, and the wing. And within that wing, whatever percentage we get for it has to be distributed between the cover skin and all the other parts. Now, for a simple case of a monocoque construction is what we are looking at in this particular geometry that you see over here. We see that the total mass is fixed for us. We can't cross a particular limit. If we are less than that, well and good. We can use that mass for something else, which is much more critical. So we can redistribute amongst the structure itself, other parts of the structure, of the same structural component or another structural component. So keeping all this in mind, we want to combine these two equations, which is what we will do next. And when we combine these two equations, we want to eliminate certain quantities, which is essentially your other design choice H. And automatically, because if you're eliminating H, your B also gets eliminated. And therefore, you end up with this particular equation. So in other words, you're replacing BH by P max by sigma U from the first equation. So BH is equal to P max by sigma U. If I substitute for that BH over here, and then I evaluate P max, or the other way around for BH, I can substitute as M by rho L from the second equation. You see that M by L I can take out separate factor, and then I have sigma U by rho. Why is M by L separate factor? Because it's not a material property, one for one. The other is, of course, L, as I said, is semi-span in this particular example, dictated by the aerodynamicist. And this is also a particular percentage of the gross takeoff weight from coming to us from the design. So we can't go beyond a particular value of that. So this is not too much of a design choice for us. Or even if it is in the case of M, it's not a material choice. The material choice is what is highlighted in blue over here, which is your sigma U divided by rho. So we've gone all around to take an example, compare its analogy with the aircraft structure, write down equations, and come up with something that we already knew, but that we had taken for granted that this is the material property that we would like to look for. But why it is so, you can very clearly see that the math is also leading to that, just like the logic led to us in the very first week. If the criterion is material failure, but as we already mentioned, that is only one of the three major criteria. And we will look at the other two criteria as well after we are done with this particular criteria. Okay, so now we are saying that if M and L are fixed, because L is dictated by the semi-span by the aerodynamicist, M is dictated by what is the allowance that we are getting as far as the mass for a wing is concerned. Therefore, we can't exceed that. So M and L are fixed. So for that given mass and given geometry, very clearly P max is proportional to sigma U by rho. And if it's proportional to sigma U by rho, then that is the material performance index for a strength-based design. So this is the takeaway from this particular slide. So are there any questions, comments, or anything that you need to understand better on this?
I don't think we have any questions for right
Okay,
now. So.
good, good. Yeah, it's fairly simple and straightforward, but just wanted to uh, go through it in a little more detail so that all aspects of it are clear. So let's go to the next slide, which is the second criterion that we will be dealing with, which is the stiffness-based design, right? So as I mentioned at the top of the previous slide, I'm not going to take the same structure for all of them. I'm going to take different kinds of structure which are commonly used for aerospace vehicles. So while dealing with stiffness-based design, we will deal with a structure like this. Remember, in the previous slide, we talked about a sheet metal. Okay, very simple geometry, uh, just slightly complicating that geometry. We will take two sheet metals now, one on the top, one on the bottom. So you see over here, so there is something called the face sheet on the top. So let me probably use my mouse over here. It might become clearer. So here, or let me, yeah. So you see on the top over here, you have one metal. Uh,
I don't know if you're highlighting or pointing at something with your mouse, but I don't think we can see it. It's just the normal slide. There's no like highlighting. There's no mouse showing.
oh, I see. Okay, we can't see that. Okay. So now can you see my cursor move?
No.
No? Okay. So use this itself. Okay. So now you see on the top. Now can you see it?
I don't think so. No.
Oh, really? Okay. You're seeing it earlier, right? When I was using the highlight.
I think I don't know. I don't remember if it was there or not.
Okay. Okay. So I'm sorry about that, but I'm sure you have it in the recording, so you can check it out later. So what I'm just showing, I'll just describe in words so that it becomes clearer. So what I'm focusing on right now is the sketch that you see on the right side, just above my video. And there we are talking about a sandwich construction in which on the top you have on the top, you have a metal sheet, and on the bottom also you have another metal sheet. And these two are used as face plates, and in between you have a lower performing material in a structural sense, what we call as the core. Okay, so end up with a what we call as the sandwich construction. Some of you might have already heard of it. Even otherwise, the word sandwich is familiar in English in terms of the food that we eat, like a sandwich. So which essentially has two breads on the top and the bottom, and something to stuff in between, right? So something very similar to that. And here we see once again we'll use the same geometry as before. And the boundary conditions is the if one end is fixed and the other end is loaded. But now instead of loading it with an axial load like what we did in the previous slide, which is uniaxial tension, here we are using a moment, which is a bending moment, which is shown in the direction here. It's a tip moment over here. And then the notations are same as before. The breadth is B, the length is L, and we will denote different thicknesses over here because once again the height is H, but that height H is split into three parts, one top face sheet, one bottom face sheet, both of which are of similar thickness. We will call that as T, and the core, which is having a much larger thickness compared to the two T's that are there on the top and the bottom, and therefore that's pretty much equal to H. To put it more precisely, it is H minus 2T is the thickness of the core, but since T is very small compared to H, it's pretty much H, that is the height of the core or the entire sandwich as well. Is that geometry clear?
Yeah, it makes sense.
Okay. So now, as far as stiffness is concerned, there are two ways to go on this route. And one is through statics, the other is through dynamics. Eventually, very similar conclusions we will arrive at for both. And but we will take, since we already dealt with a statics example on the previous slide, as I said, we want to introduce as many concepts as possible through the same slide. So we want to look at dynamics over here. So both are stiffness-based designs, and both are achieved simultaneously. So once you have a stiffness-based design which is done appropriately, what will happen is those arrows that you see over there refer to a very large reduction if it is going downwards, or very large increase if it's going upwards, right? So here in statics, what we want is we want the deformations to be as small as possible. That's why the arrow downward. Whereas in dynamics, the goal is to keep your natural frequencies as high as possible. Remember that this is a continuous structure, unlike the spring mass damper or spring mass system that I mentioned in the previous while discussing a previous slide today. which is a single degree of freedom system, or you might have seen pendulum or even multiple pendulum or multiple masses connected to various springs, etc., leading to 2, 3, or 4 degrees of freedom, all of which are essentially finite degrees of freedom. Whereas here you have a continuous system, each point can move independent of the others to some extent, which means you have an infinite number of points in the structure, and therefore it's an infinite degree of freedom system, which is a continuous system, and therefore it will have multiple natural frequencies. Remember that the in the case of the single degree of freedom system without damping, we said that it is just square root of k by m. That is something that you're familiar from high school physics as the natural frequency, and it's a single natural frequency. If it's a 2 degree of freedom, it will have two natural frequencies, whereas here a continuous system will have infinite natural frequencies. But not all of them are of importance or even relevance, even from a very detailed design or detailed analysis point of view. But the first few are. So the first few natural frequencies, starting from the lowest of them onwards, it's important, and the corresponding so-called mode shapes. And also it depends on the kind of deformations that it undergoes. So if you take this wing, for example, it can go up or down. That's essentially bending. It can go forward or backward, which is much more predominant in the case of the helicopter, but here also because of the drag, which we call as the lead lag. This is called the flapping degree of freedom in the case of the helicopter. This is called the lead lag. And then you would have the torsion. So these are all the kinds of uh, curvatures that result because of the moments. Two of them are bending moments due to lift and drag. The other is the torsion due to the pitching moment, and which will twist this entire structure, right? So now our focus is not on torsion. Our focus is not on extension like in the previous slide. On this slide, we are focusing on a tip bending moment. In reality, you'd have a bending moment distribution throughout the span or semi-span, and then you'll have to take that into account in an appropriate way. But the end result, as far as the material property of concern for us, will continue to be the same. So we might as well, for this undergrad course, take a simpler geometry like what we are talking about. Now, why is it that we want to keep this natural frequency high? The idea is that, remember that there are dynamic loads coming onto the structure. We already discussed them quite extensively in two of the classes. In fact, we dedicated to that, or rather 1.5 classes. And so we know that many of the loads are time varying. They could be in the form of impact, they could be in the form of fatigue, and various other problems like vibration, etc. So in each of those cases, there is a possibility that the loading frequency might be close to one of the natural frequencies. If it is so, then typically you can end up with resonance, and these have resulted in some really disastrous accidents for various vehicles, in particular helicopters, through what are known as ground resonance. Just a helicopter on the ground with its main rotor switched on, the power to the main rotor, and therefore it's rotating, and suddenly it breaks apart and falls. It has not even taken off. So that's what was the result of so-called ground resonance. Doesn't happen, of course, these days. So for many decades, we have been able to master that, to avoid that rather. And similarly, something like that can happen in the air while the aircraft is flying, either hovering or even when it is cruising or flying in different directions. There's a possibility of a certain resonance occurring called air resonance. So ground resonance and air resonance were very, very severe problems for some of the earlier helicopters, no longer so. One reason for that is this kind of stiffness-based design, taking into account that the natural frequencies are designed in such a way that they are well beyond the typical dynamic loading frequencies. Because especially in helicopters, we know that the RPM at which the rotor blades are going to rotate, both for the main rotor and the tail rotor, depending upon the aerodynamic design. And therefore, multiples of that frequency are the loading frequencies coming from the aerodynamics. So if it's rotating at a particular, let's say 100 RPM, you can convert that to hertz. That's per second, number of cycles per second rather than instead of revolutions per minute. And therefore, you know the particular forcing frequency. And multiples of that are the forcing frequency because sinusoidal and cosine loads coming from the aerodynamics are altering this. Because it's very, very interesting. Some of you might be aware how helicopters fly in terms of the overall qualitative controls that the pilot has. Of course, he has the rudder pedals, which make the helicopter to yaw. I forgot to bring a helicopter model over here, so I've just demonstrated the Beluga. So essentially, when the stick is pushed left or right, then you essentially have a roll, and then if the pedal is moved, you have the yaw, and then if the pitch stick is moved front or back, then you have the pitch. So this is as far as a fixed wing aircraft is concerned. On the other hand, in a helicopter rotor blade, you have two sticks. One is called as the cyclic pitch stick, and the other is called the collective pitch stick. So the collective pitch stick, when you lift it up, typically for a right-handed person, it will be on the left, and essentially you're lifting that stick. You are essentially, for all the rotor blades, it might be a four-bladed rotor, for example, all the rotor blades will increase their pitch by the same amount. In other words, they will change their angle of attack by the same amount. And when they do that, what happens is the essentially, let's say we are increasing the angle of attack and we are still below stall for the airfoil which is used. So essentially, all of them are lifting up, which means that they are all bending upwards. So when they are bending upwards, the cone angle increases, and essentially the overall lift increases, and the helicopter is able to climb upwards. So in other words, able to accelerate upwards, and therefore it can go up. If you're decreasing the pitch, then the cone angle reduces and the helicopter comes down, right? So that's as far as the collective pitch is concerned. Now coming to the cyclic pitch stick, when you're trying to move it forward or backward, now it's a little more non-intuitive because there is a 90-degree phase lag between the pitch and the flap. So pitch, remember, is the change in angle of attack that is happening over here, to put it in very simple words, though there is a slight difference between them. Then coming to the, that is the pitch, whereas the flap is the entire rotor blade going up or down, right? So now these two are coupled with each other aerodynamically by 90-degree phase lag. In other words, if I, in the helicopter, if I'm increasing the, let me I think this should be visible there. So if I'm increasing towards my right, I'm increasing my pitch. Then only when the rotor blade comes to the forward, then the flap will become maximum. So in this case, on my right side, I'm increasing the pitch. Right side, I'm increasing the pitch. Then when I go forward, the flap will become more. So by increasing the pitch at the right, what I'm doing is in every cycle of the rotation, I'm making the blade at the front go up. Similarly, the blade at towards the this end, that is essentially to my left, will have a minimum pitch so that the rotor blade at the back, when it the same rotor blade when it goes to the back because of the RPM, then it goes down. So essentially, the tip plane of the rotor blades is having a tilt towards the back, and therefore the net thrust from the helicopter rotor is not only having a vertical component but also a slight horizontal component towards the back, and the helicopter will start moving rearwards. So similarly, you do exactly opposite to tilt it forward and move it forward. From a pilot's point of view, it looks very, very intuitive that he's pushing it forward. The helicopter moves forward. He's pulling the cyclic pitch stick. The helicopter moves back. He moves it to the left. The helicopter moves to the left. He moves it to the right. The helicopter moves to the right. But the actual mechanism by which this happens, both the control system and eventually the aerodynamic coupling between the pitch and the flap, is very, very interesting over there. So since this is the situation, you can very easily see that if there is a coupling that is happening between the natural frequency of the blade and the dynamic loading frequency that is coming because of the aerodynamics, because of these changes in pitch, etc., then you can see if they're close to each other, resonance can occur either on ground or in the air, and that could be quite disastrous. Though I explained this for a helicopter because it's much more dramatic and easy to kind of visualize. Similar kind of less dangerous situations exist with the aircraft as well. And going beyond, as we'll see in the next slide, though we will talk of elastic instabilities there. There are aeroelastic instabilities like static divergence and or flutter, which are certain complex versions of this. Similarly, of course, the aeroelasticity of the helicopter is even more complicated. So, whereas these resonance problems are more or less tackled, the aeroelasticity problems are still under research. A lot of them, there's still more room for optimization over there. And interestingly, the other instructor that is there for this study abroad program, Professor Mayuresh Patil, his one of his major areas of expertise is aeroelasticity for fixed wing, high altitude, long range hail aircraft, as well as medium altitude, long endurance kind of aircrafts. So, those of you are interested in knowing more details about it, utilize the time that you spend with him uh, out of class also to uh, discuss some of these topics because these are extremely interesting for us aerospace engineers. So it's very clear that whether I take the static path or the dynamic path, I will come up with a particular material-based criteria, which is for stiffness-based design. And since we already dealt with statics, we'll now go forward and deal with dynamics. And the boundary condition I already mentioned to you is cantilever. Then the geometry is thin-walled. In other words, your H, that is the overall thickness, is still small compared to B and L, just like in the previous slide. Because that's the overall geometries that we are familiar with for most high aspect ratio wings and also rotor blades. So it's thin-walled. And unlike the last time where we had sheet metals, now we have a sandwich beam again because B is small compared to L. Not only is H small compared to B, but B is also small compared to L. So in addition, there's another small geometric parameter, which is within the thickness itself, as I already mentioned, that because we have three layers to it, a top face plate, a bottom face plate, and in between a core. Now, each of them have different thicknesses. Both the face plates have a thickness T each, and therefore that T is very small compared to the overall thickness, and therefore H becomes approximately the core thickness itself. Uh, and then here, as far as the core is concerned, the choice of the material is such that since it doesn't take much of the load, we want to take a material whose density is very low and therefore its mass is low. And of course, as a natural fallout, you'll see that the stiffness and other structural performance parameters are small as well. But doesn't mean the core doesn't do any structural function. In fact, while the face plates take all the tension and compression coming because of this bending, remember in the direction in which we have shown the bending on the right hand side over here, we see that, ah, now I know probably why the you're not able to see that. Let me see if I can stop sharing, share my entire screen. Maybe then you'll be able to, which is what I did last time. Okay, let me see.
Yeah, we can see your cursor now and
Oh,
the
wow.
highlighting.
Okay. I'm really sorry. I just shared the window, the PowerPoint window, then this was not coming up. But now I'm sharing the entire screen. Okay. So good. So now, as you see here, there are three layers. A very thin layer on the top is a top face sheet. A very thin layer at the bottom is the bottom face sheet. Each of them have a thickness small t, denoted by small t, whereas the overall thickness is h, and that is large because the core thickness is large. Therefore, we use the same letter without loss of much accuracy for the overall thickness of the sandwich as well as the thickness of the core itself. But in reality, they differ by a small amount, 2t, which is twice because there are two phase sheets. Okay, now coming to the direction in which I have drawn this moment, which is opposite to the one that you would find in a cruising aircraft, which will typically be bending upwards to lift the wingtip up. Here I'm showing it downwards over here, let's say in a particular maneuver. So it's actually going down. For example, we are focusing on some point in the bottom half of the VN diagram that we discussed, the flight envelope. So then you would have there is a possibility of a moment in this direction as well. So when you have a moment like this, it's very clear that the top phase sheet, um, let me see. Yeah. You can see the highlight as well as the arrow.
Yeah, we can.
Oh, good. Okay. So now you see that when the moment is applied in this particular direction, then you see that the top sheet is getting pulled out, which means there is tension in it, and the bottom sheet is getting pushed in, which means that it is under compression, right? So if that is the case, then there is an axial load along the x1 direction, along the length. We'll use the same notation like last time. Along the length is x1, along the breadth it is x2, and along the thickness it is x3. Similarly, the unit vectors are b1 along this, along the breadth it is b2, and along the thickness it is b3, though I have not shown them explicitly over here, right? So now it's very clear that the top is undergoing tension, the bottom is undergoing compression. Both are normal stresses. And the difference between them, in this particular case, it's a pure moment. So there is no shear force that is there. If you draw the shear force diagram for this beam from the fixed end to the free end, you will see it will be zero throughout. Whereas if you draw the bending moment diagram, it will be a line parallel to the x-axis, which is a constant value because there's a tip moment over there, right? But in reality, what will happen is you don't have a tip moment, but a lift distribution, which is going to cause a shear force apart from a bending moment, which is going to vary along the length. So bending moment diagram will not be as simple as a straight line parallel to the x-axis. So in that case, the core also has a structural performance required out of it, which is to take that shear force. It resists that shear force coming because of the lift distribution or even the drag distribution through what is known as a transverse shear stress. Okay, so that's beyond the scope of this particular slide. So we will not discuss that over here. Our focus, because even if it is there, then the value of that shear stress is very, very small compared to the stress due to bending, that is the axial stress in tension or compression in the top phase sheet and the bottom phase sheet, which is the dominant one, even in the real situation of an actual lift distribution. So coming back to the simple problem of just the tip moment, here we see that the core is made out of a material of very low density, and therefore the overall mass is small. Its stiffness is also small because we don't want too much of a stiffness over there. In any case, it's not taking the tension or compression, which is handled almost entirely by the top and the bottom phase sheet, right? So that being the case, we can now introduce a geometric feature that you'll be already familiar with, called the second moment of area. But unfortunately, over a period of time, a lot of books as well as instructors started using the word inertia for this moment of inertia. In a sense, it feeds into inertia, but it's not inertia by itself. So you have to be a little careful. So this has the unit of meter power 4, essentially a dimension of L power 4, uh, because it involves BT here and a H squared. So this is an approximate value for this because the contribution from the core is very small towards it. It's only the top and the bottom phase sheets which contribute. And their cross-sectional area is the breadth of each phase sheet multiplied by the thickness of each phase sheet to give the cross-sectional area of each phase sheet, which is BT. And since there are two of them, it is 2 times BT. And each of them are a distance h by 2 away from the midplane of this structure. And therefore, it is h by 2 squared. So that's the moment arm, which is essentially squared over there. So it's the second moment of area that you're looking at. So you have the area and multiplied by the distance of that area, CG, or centroid rather, from the uh, centroid of the overall cross section, and that's what you end up with. Now, this is an important factor. Now, we will look at why it is important in a later class, but right now, let's take it for granted that in a bending problem, this is one of the geometric features of great significance. In fact, we discussed this qualitatively when we considered why we have I sections, that is, for a lot of beams undergoing flexural load as the major load, we have the I section as a dominant geometry because we want to push the material away from the center or so-called neutral axis so that it can take much more stress and therefore counteract much more bending moments, much larger bending moments. Okay, another quantity again, once again, we are dealing with aerospace structures or any vehicular structure for that matter. It is a light-weighted structure and therefore mass becomes critical. And here we are talking of a mass distribution along the length. But since it's a prismatic structure, it doesn't matter. It's a constant all through. That mass is, of course, the mass density, which is in kilogram per meter cube, denoted by the Greek letter rho, like in the previous slide, multiplied by the cross-sectional area, which is the breadth times the thickness of the face sheets times 2, because only they are contributing to the dominant quantity to the mass, because as I already mentioned through this arrow, downward arrow here, that the core mass is very small because the core's density is very small. So in other words, if we had rho C and rho for the face sheets, then that rho C will be very small compared to rho, and therefore this is all that is really mattering. Okay, so it is because there are two phase sheets, is 2, and because it's mass per unit span, I'm not multiplying explicitly by the length. If we do, we will get the total mass. So instead, we are multiplying by 2bt, which is the cross-sectional area. bt for the top phase sheet and bt again for the bottom phase sheet. So now, again, we are not doing the derivation here, a little more involved. So you'll have to take it from me or from Bausho. If you're VPN, you can download Bausho's book and look through that particular um, equation that he has given, or rather a proportionality. And he has also referred it to another part or section of the same textbook where, and it's a big textbook, by the way. So it's not meant for this course alone. It's meant for a few courses, and therefore he has combined all of them into a single book, and therefore he can cross-reference some of these derivations, which are beyond the scope of this particular course, an introductory structural analysis course. So what we are interested in here is the natural frequency omega. And instead of giving an equation which involves many other parameters, we take only those parameters of interest to us over here. The first factor is 1 by L, where L is the length over here, and that is L not by itself, but L squared. And you would see something similar to that in the so-called uh, buckling as well, because this is something with respect to time, whereas buckling is with respect to space. Again, there's a beautiful analogy between what happens in dynamics and what happens in elastic stability problems. Just replacing time and or interchanging space and time, we can arrive at a lot of equations. So that's again probably for another day or another course. So what we have here is, so the reason why I brought up that analogy is some of you might have heard of the Euler buckling formula, which is pi squared EI by L squared as a critical load for buckling. And there also you have a denominator L squared that you see over here, which is very similar to what you have for the natural frequency here. And the other thing that we were discussing earlier today, for a single degree of freedom system, we saw that the natural frequency is just one of them, and it is given by square root of k by m. And this power 0.5 is, as you know, nothing but a square root, and therefore, and m is there already, but instead of actual mass, we are talking about a mass per unit length, which is the unit span in this case. And on the top, instead of the spring constant, linear spring constant k, we have the so-called bending stiffness EI. Why is it the bending stiffness? We shall see either towards the end of this week or in the beginning of next week. We will see what is the significance of that. But essentially, there's a material parameter E, which is the Young's modulus, and the second moment of area, which we talked about here and erroneously called as moment of inertia by most books, and therefore I've used the same notation, and which is why they use I as well. But yes, it does contribute towards inertia. So from that point of view, at least there is some credit to it. But truly speaking, it creates more confusion than helps. But just be aware of this. Okay. So essentially, so you're looking at a square root of k by m kind of a factor over there, just that because it's a continuous system instead of a single degree of freedom system or even a finite degree of freedom system. In fact, it's an infinite degree of freedom system. It will have many such natural frequencies, which is why I qualify this by saying it is the first. And amongst the mode shapes, there will be natural frequencies in, as we already demonstrated over here, in natural frequencies in bending in one direction, bending in the other direction, torsion, and axial direction as well. So keeping all of that in mind, and each of them will be infinite. So it's 4 times infinity, which is also, of course, infinity. But just to qualify each of them, we need to make sure not only by the number, say first, second, third, etc., but also say what is the mode shape if it is uncoupled. There are some coupled natural frequencies as well. So, in other words, the bending alone may not be happening by itself. Bending and torsion might be happening simultaneously with the same period. And so, therefore, there could be a coupled natural frequency associated with that of flexural bending with a torsional, flexural torsional kind of a mode shape that you could have, for which there could be a natural frequency. So, right, one of the important things amongst those infinite number of frequencies, only finite number is important, and the first few are much more important. And amongst the first few, it's the bending along the direction caused by the lift. So, in other words, the lift is bending it up or down, making the wingtip go up or down. So that's the kind of bending, rather than the one which makes it go forward or backward along the chord. The one which makes it go up or down along the thickness is what the one that we are interested in. That particular first bending natural frequency is what is given by this particular relation that you see. The others, expressions will involve these quantities, but in a slightly different manner, and some different factors will be involved. In any case, we are dealing with only proportionality over here. Okay, so are these three inputs clear? I'm sorry, it's beyond the scope of the class to go into this derivation, but you can check it out. And if you have any doubts or questions, you can always interact with me separately beyond the class hours. Um, is this clear so far?
I think it is clear. But I
Okay,
have one question. So in the
please go
second
ahead.
one,
Yes.
it's mass over UT span. What does UT stand for?
Uh, the second term over here.
No, the line above that.
Okay, 2 rho
Mass.
BT.
No, on the left side of the equation, where it says mass over UT span.
Oh, yeah,
Or
unit span. So I'm just saying the mass per unit length. So this is, remember, half the span. So coming back to our aircraft, so you know that the distance from the tip to the tip is the span, right? So half of that is the half the span. So I'm saying per unit span means this span could be, let's say, 3 meters. So I'm saying per meter. So per unit span. So UT stands for unit. It's just I'm just lazy to write it out as UNIT. So I'm just writing it as UT to keep the slide also less crowded. So glad you brought it up, because others may not also have understood that. Is that clear now?
yeah,
Yeah. So it's a, see, if I written it as the total mass, then I have to multiply this by L, which is the length. Then I get the total mass in kg. But now I get this right hand side in kg per meter. And therefore, M also as the unit of kg per meter. So M over here as the unit of kg per meter, it's mass per unit length. And that length that we are talking about is along the x1 direction, where we have the total distance of half the length of half a wing is L. And therefore, it is mass per unit span over there. Yeah.
yeah, I got it.
Yeah. Any other question from anybody else?
No, I don't think so. No other
Okay.
question.
So now we can combine these two equations like we did in the previous slide, one for the mass, the other for the natural frequency. But in the natural frequency, we can also substitute for I. So we have an expression for I here. We have an expression for M. So I can substitute for I and M and simplify this whole thing. Then you can see that this is what you eventually end up with, that the remember that we're not talking of an equation here. The last two bulleted points are both proportionalities. So I might have dropped off a few more terms which are not of relevance for us from a choice that we are making for the geometry and or the material. Okay. So once again, we have two factors which are multiplying each other. Uh, as you see in this particular thing. Here you see the first factor is h by L squared, which is a geometric factor, and the second factor is E by rho to the power half, which means square root of E by rho, and that's involving only material properties, both E and rho being material properties. So just like in the previous slide when we were talking about the strength-based design instead of stiffness-based design, there is an influence of geometry and an influence of material as well. And there also we wanted to maximize the failure limit. Here we want to maximize the natural frequency so that we will avoid it matching with any of the dynamic loading frequencies and avoid things like air resonance, ground resonance, etc. in helicopters and similar kind of uh, potential accidents in the case of fixed wing aircraft or any other flying vehicle for that matter, which means that either I can do it through increasing this first factor through geometry or the second factor through the material. Let's focus on the geometry. Once again, L is involved here, which is the semi-span, which is something the aerodynamic team will never allow me to change because that is something that we need uh, from a particular planform area which is required and the other aerodynamic requirements. So we will not have any room to play around with L. But we do have a way to play around with H. I can increase my H, but obviously when I increase my H, you know that the overall mass will increase. But since the core is having very low density, it may not be that much of a weight penalty because the more of the weight, as you see, is coming from the face sheet, which has a much larger density. And therefore, it might be possible in some cases to make the core thickness slightly larger in order to push this up if already you have chosen the material with the largest square root of E by rho amongst the choices of materials that you have for a particular component, because there are many other criteria based on which the component has to be chosen. So now that if you fix the geometry, because as I said, today's class focuses primarily on the materials. So the geometry is fixed. So h by L squared, the first term in the previous equation or proportionality is fixed, and therefore only the second term comes into picture, which is entirely material based. And therefore, we have the material performance index uh, for stiffness based design, which is square root of E by rho. Okay, so E by rho power half is what we are looking at. In the one of the initial classes, I had said it is just E by rho. Okay, so it's quite clear that if I'm comparing two materials, one has a larger E by rho compared to the other, it will have a larger square root of E by rho as well, because for most materials that you're dealing with the kind of units that we deal with, these are quantities which are larger than one, and for any number which is larger than one, if one set is larger compared to the other, its square root will also be larger. Whereas if it is less than one, the opposite happens. But here, what we are saying is that because we use dynamics as a criteria, we got that power half. If we had used statics as a criteria and tried to minimize the deformations, we would have come with the same performance material index, but without this square root, and therefore it would have been just E by rho. But since flying vehicles, like any other transportation vehicles, are dynamic, experiencing dynamic loads and in fact, very critical dynamic loads compared to even other transportation sector vehicles. Therefore, this is a more appropriate quantity to compare. What it does is, in fact, reduces the level. For example, two materials are differing from each other by a factor of 9 as far as E by rho is concerned. Square root of E by rho will differ only by a factor of 3. So the advantage will kind of slightly come down, but you'll still find one material more advantageous than the other based on this criteria as well. Okay, so is this clear in terms of extracting this particular criteria over here, E by rho power half for the material?
Yeah, it makes sense.
Okay, thank you. So let's go on in the last few minutes that we have. Yeah, maybe I'll just stop with this slide, which will be kind of a preamble for the uh, next class, that is tomorrow, a live class, because I'd like to actually draw a few things on the whiteboard there, a little larger, though I can use the whiteboard on this. I think since we are just 10 minutes left, we will probably do that in the next class. But just go through this particular slide. It is there in the files section as well. And of course, it will be on the video. Just go through this and see if you can answer this question in tomorrow's class, and then we will take it forward from there. Thank you. Bon appetit. Ignore this, what you see on this bar chart over here, because that was, and all these numbers. This was for a particular class that I used this slide for the first time. So I'm just, it's a legacy from there. So it's the number of students who answered each of these. So that will kind of give you a kind of feel for how divided the class was in terms of answering this particular question. So it's a nice thought-provoking question. So even with the amount of information that you have already had from the deformable bodies course and the statics dynamics course, and especially this course, the last 10, 12 hours that we have had classes for, some of these questions might be clear to answer. You might also want to leverage some of the things like, so this is not an assignment, by the way. It's just a question that I will ask in class. So don't think of this as an assignment that you need to present. But we will just exchange, interact, and I'll get inputs from you before uh, giving you the appropriate takeaways from this particular slide. The reason why it is introduced at this particular stage is because it's the third criteria that we want to go to, stability-based design. Remember, we already finished strength-based design, and we finished the stiffness-based design. Now we want to get into the third S, which is the stability-based design, which is not commonly dealt with in most courses, even at the graduate level. But I'm glad Posho dealt with it at an undergraduate level, and so do I, because it's a very important criteria and it should not be missed. And at the level at which we are introducing it in any way, we are not going through the full derivations. We are only presenting the intermediate results and the final result. And therefore, it is something that is still graspable at the undergraduate level. So before we get into that stability-based design, if you answer this question, then that will be understood a little better, which is why this is important. So if some of you have gone through, for example, Mohr's circle, etc., the concept of Mohr's circle in deformable bodies, then you might use that for some of these things in order to understand it better. But if you don't bother. I will discuss it in class tomorrow. Thank you.
Do you want us to answer it now or in?
No, no, let's do it at the beginning of tomorrow's class. Okay. Okay, we're done with the class for now.
Thank you so much.
Thank you very much. Yeah, bye. See you.